אוקיי, אז אנחנו ממשיכים היום בחלק השני של somato sensation. מה? Yeah, sorry. Honest mistake. Okay, so we continue today with somato sensation. I think we haven't finished yet exactly the first lecture, but I will briefly go through the things, and if you think that we missed something, please let me know. We have lots of stuff today, so I'll try to be a little bit faster. So we're going to continue to talk about just briefly what happens when we go from the receptors towards the central nervous system, and then the first half will be devoted to what happens in the cortex, and then I'm going to go to a very specific system which is called the visual cortex, which is specific to rodents, and we will explore that system in a little bit more detail. So just to remind you what we were talking about, we said that somato sensation is a complicated system in the sense that it is not one sense, but it's several. It has several modalities. It has touch, proprioception, pain, and temperature, and we actually mainly talk about touch. And we said that we can classically separate it into four stages. One is a transduction, the transmission of the information, integration, and perception, and we basically stopped about here, and we're going to cover somehow these two today. Okay. So to remind you, the basic process is starting with some sensory organ, which could be we talked about four types under the skin, two which are superficial and two which are deep, the fast adaptive and the slow adaptive, and then these receptors are sitting at the end of a nerve, an axon actually, and the spikes are initiated at the terminal, and they're traveling backward toward the cell body, but and actually continue on the axon. The cell body is located in this dorsal root ganglion, which is outside the spinal cord, and then they go through the dorsal horn, and they might make a synapse or might not, but they also continue to go up. You can see it better here. They go up in the spinal cord. At some point in the medulla, they cross the midline, and then they go toward the thalamus, and from the thalamus they go to the cortex. In the cortex, we'll talk about it a little bit later today. Okay, so this is the route that the information is flowing from the skin in terms of touch to the brain. We said that there are different types of receptors. Some of them are slowly adaptive, which means that if you give them a stimulation which lasts for a long time, they will continue to spike during the stimulus, and they might change the frequency with time. They also increase the frequency with the intensity of the stimulus. So the strongest the stimulus is, the faster the firing rate. And there's a different type of receptors which are rapidly adaptive, and they react more to the derivative of the stimulus rather than to the stimulus itself. So when the stimulus starts, you will get a spike, and when it ends, you get a spike, but in the middle, you don't get almost anything. If you have a slowly ramping input, you will get spiking during the ramp, but then afterwards, you wouldn't get anything. Okay, so these are the two different types, and we said that the receptors are also, the information is carried out by different type of axons. Some of them are myelinated, which are fast conducting, and even those are actually separated into three groups: the A alpha, A beta, and A delta. And there are the C fibers, which are unmyelinated, and they are very, very slow, and they carry information mainly about temperature and pain. We also said that the spinal cord, and here I'm not sure how much we went into the details of that. I don't remember if we managed to cover it or not, but the spinal cord is actually segmented into different segments, and information from different parts of the body is conveyed through different segments. And each segment actually has its own dorsal root ganglion. Okay. I think that's the main thing that I wanted to talk to you about. And the last thing is that we said that information from each segment is actually carried out separately all the way. So for example, if you follow three axons that are entering into the spinal cord through different segments, so this would be, here would be one dorsal root ganglion, here there would be another one, and here another one. Each one of these actually travels separately as a different pathway all the way to the thalamus, and then in the thalamus they would also still arrive into different areas and will be sent to different areas on the somatosensory cortex, which actually reflect the somatotopic map. So the fact that the hand is represented on the cortex from on a different location than, say, the face or the back or the legs. And we talked about this little homunculus that is mapped onto the cortex. Okay. Why is it not moving? Okay. Okay, I'm going to skip this one because I think Alex is going to talk to you about that. And now we're going. So we kind of covered the path to the cortex, but now we're going to talk a little bit in more detail what happens during this path. And I want to start with Adrian. I don't know if you have ever heard of him. Did you? Anyone? Well, okay. So Adrian should have been here on the first lecture of this course. Is considered in a way the father of neural coding, if you like, and he was working at the early years of the last century. He won a Nobel Prize, and as all Nobel Prize, the lectures during the prize are on the internet, so you can actually read his speech. And he was studying the frog, so he was studying actually the nerves coming out from the muscles of the frog. So in a way, it's somatosensation, but it's more related to proprioception, which is the thing that we're going to talk about next semester. But in any case, he came up with this. So we talked a little bit about this phenomena. I'll show you a similar slide very soon. The idea that the frequency is actually carrying out the intensity of the stimulus is his idea. It came out from his experiment, from this experiment, and it's a very, very fundamental notion in neural coding. So information, you've seen it also many times, of course, in other courses and in other lectures, but this is why it started. And just to show you how it started. Sorry, this takes a little bit of time. So he was using this phenomenal amplifier So the idea was the following: you have the muscle and you have the nerve, and he would put two different electrodes on the nerve. So now this is a nerve, not an axon. It's not a single fiber. It's a bundle of many fibers that's coming out of the muscle, and he can actually what he could do is change the length of the muscle. This would be the stimulus. Like stretching the muscle would be the stimulus. And there was a bunch of electronics, if you can call it that way. And at the end there was this mercury lamp, which actually it's like a temperature meter, and the height of the mercury would kind of encode the voltage that he records between these two locations. And then and he would basically take a movie that would also at every time would kind of picture the mercury lamp, and this would give him something like that as a so the level of the mercury as a function of time. This is the way he was recording things. And then after he had these movies, in a way, so like on a strip of paper, he could trace them. Okay, and what he found out, and it's kind of, I never actually understood how he did that, but he found out that the nerve is actually an all or none phenomenon. So it's conducting something that is all or none. And you can see it here in a way, but it's not so easy. You can also see it somehow here. The idea is that you have these burst spikes, but we know that it's not like one axon. It's a bundle of axons, and it's probably what he was recording is something similar to this A alpha fast-conducting axon. But nevertheless, he understood, first of all, that the information is traveling in an all or none fashion, and secondly, that is the frequency is related to the amplitude that he would apply on the nerve. And then he came up with like this idea that I showed you before, that the amplitude is encoded with the number of spikes. So basically, the amplitude is translated into a potential that causes action potentials. And then if you record only the spikes, that's what you get. You get like spikes that encode the duration and the amplitude. And again, so the amplitude is encoded by the frequency of the spike. Okay. So if you follow a single axon, you can actually record what exactly happens on this receptor in terms of like the intensity of the stimulus, the duration of the stimulus, and this is quite obvious. But this does not continue all the way in the nerve system, and you all kind of going through, I think, neural networks and stuff like that. So anything that I will put here would be a very sort of caricature of that in some sense. But the idea is that there are two main processes that happen. There is divergence and convergence of information. At some point, the axon that comes from a receptor, and we saw the first example of that we saw already in the skin, where there are the superficial receptors. You remember, they don't each one sit on a separate axon, but they actually combine together to one axon. So it's sometimes difficult to tell exactly where the stimulus was, just because when you touch, when you activate a single receptor, it will activate the same axon as another receptor that sits in a different location. And just by looking at the axon on this single axon, you cannot tell which of these two receptors was activated. Okay. So in order to do that, you can do two things. One is look at different axons, right? And then this different axon has different distribution, and only the ones that will co-localize on the same area will spike together, and this will tell you something about the location. And this is the idea of convergence. Uh, but at the same time, you also have this divergence. So, for example, what we look here is on a caricature of a location which happens somewhere in the spinal cord, or maybe later. I mean, and then again and again during, all the nervous system. The idea is that you have neurons that are sitting in this area and receiving information from the skin, and the information comes, on a single axon, but then it splits and makes synapses on many neurons. So when this area is activated, or when this receptor is activated, all these three neurons would receive excitation. So this neuron would be obviously activated when this area will be touched, but also when this area will be touched, because it will get the information from other neurons that are less directly related to the area that it's connected to. And then this information is then split out. In this case, you don't see it, so the idea is like each one of these axons is now traveling on its own. But of course, at the next station, they will do the same. They will split and activate other neurons. So you have this divergence, and at the same time, you have convergence, because so this would be the divergence, right, where the axon is split into three. But this will be the convergence because it gets input from different locations. Okay, so you have integration and you have separation. And this is basically the whole trick. Okay, or at least that's what neurophysiology thought to be the whole trick, until physicists came up with ideas like attractors and all kinds of things like that. But the naive idea is that everything in the nervous system is now computed in this way of divergence and convergence, almost, except we have another thing to take into account, which is inhibition, and there are different ideas here. I think there is a flow in this figure, so I don't want to talk about it too much. But this one at least kind of separates the three main concepts. And I think you probably covered some of them, but the idea is that there is inhibition which is called feed forward. So if you have a neuron that transmits information, this would be, say, an excitatory neuron transmitting information from the medulla to the thalamus. Okay, so this is a thalamic neuron, and this is a neuron in the medulla, and it carries out excitatory information that arrives to this neuron. But on the way, it can split up and activate an inhibitory neuron that will inhibit another neuron. Okay, so this would be a feed-forward inhibition. The inhibition is coming on the path of the information. Okay, there's also feedback inhibition. So this neuron now can, once it is activated, can activate another inhibitory neuron that will inhibit this neuron. So this would be a feedback inhibition. And then there is also descending inhibition, so inhibition that's coming from stations that are coming up in the hierarchy and sending information to activate inhibition. So, for example, if the cortex wants to ignore some type of sensory information that's coming from the body, it can inhibit this information by descending inhibition. So this is what we call descending inhibition. Okay. So we're going to see now. So this is a very classical view, okay? And now I want to show you a paper that actually show an example that a little bit challenges this idea. Okay, so this is an experiment that was done in 2004, and you can download the paper if you like. And what they do is the following. They do it in humans. I already told you that you can record from afferents that coming from the skin in humans. So you basically record from the nerve in a person. And what you do here is that they have this device that basically can push on the finger, but it can push in different directions. So it can apply the force either directly into the finger, which would be the normal direction, but it can also go right and left and up and down if you want. Okay? So it has 5 directions. And then also they can play a little bit with the shape of this device. So they can use a round tip with different diameters or a flat tip. And then they apply the force. Sorry, the device doesn't do anything. Then it advances towards the finger, and then it stays there, and then it moves back. Okay, so you have like this, and then it repeats itself again and again and again. And they record from different afferents, and they map. What they show you here is each dot means there's an afferent that we recorded from so the first of course map was what this afferent responds to. Okay, so these are the afferents that they're recording from. And there are different type of receptors and afferents, as we talked about: fast adaptive, slow adaptive, and this is a result that is a little bit kind of different to what we usually expect. So I was telling you that these receptors will respond with different firing rate depending on the amplitude of the stimulus. But what they see here is that it's not only the frequency that could change, but it's also the latency to the first spike. So what you see here is it's different directions, okay? And you can see that in one direction, the afferent in this case. So these are 2 examples of two different afferents that they recorded from. So you see it like from like that and like that. Okay, it's the same location, but shown in two views. And this is another one. And these 2 examples of fast adaptive type 1 receptors. And what you can see is that the time where the first spikes occur is different in the 5 different directions. Okay, and also in this one it's a little bit less clear. Okay, but in this one is also kind of you can see that these 2 directions are first, and then comes this direction and this one, and we'll look at it a little bit later. Sorry. So yeah. Okay. Okay, so if you take now a few examples for each one of these types of fibers, you can see that each one of them has some kind of curve that represents the latency to the first spike. So, for example, in this case, this direction, which is down for that sense, okay, is the first spike occur on this direction, okay, and for these ones it's different ones are different, but each fiber has like its preferred direction, if you want, as a latency for the first spike, and it has some variability in its latency to the first spike. Okay, same here. So basically what you should take from it is that they're not flat. It's not like the first spike always occur at the same time. And what matters is the frequency, just as we talked about from the classical ideas of Adrian. Right? He wouldn't kind of care about when the first spike arrives. It just what we care about is how many spikes we get. So to say it's not completely flat, and this is in milliseconds. It's quite, it's quite significant difference between like 70 milliseconds and I don't know 10. Okay. So now they did two things. One is less interesting. I think this is what you see here, but maybe some of you would find it interesting. The idea here is that they take a bunch of, or basically all the fibers that they can that they recorded from, say from the fast adaptive one, and they say, can we encode the direction as a function of how many fibers we can rely on based on the first spike. Okay, so the idea is that we take only the first spike, and there is some information you saw there is information we know for each fiber what direction it prefers with the first spike, or what the shortest latency. Can we actually use that to predict what the information, what the direction was, just based on the recording, relying only on the latency? Okay, we take only one spike from each fiber, and we say this is enough for us. Can we do that? And you can see that they can actually go to pretty good probability of decision, and it also takes quite a little time. You know, within 20 milliseconds, they go to the plateau, to the maximum information that they can reach. Okay, and then they come up with this idea where the following thing, with the following idea. Okay, so let's say that now I apply two different stimuli. One is a red one, which is a convex one, and one which is flat one. Okay, and it applied to the finger, and each one of the, there are many receptors here which are responding to the stimulus, and they would respond with different latency with these two stimuli. Okay, so they would, so for example, this receptor here, okay, say here, would spike first for the blue stimulus and later for the red stimulus. Okay, now, and also between different receptors, there will also be some variability. And now all this information is traveling through the nerve to the spinal cord, and at some point it's get integrated. So we talked about it, right? It's kind of getting converged onto other neurons. And here the idea is the following. So some neurons will happen to be such that the spikes from, a subgroup of the axons will arrive at the same time. Okay, and then they will get three spikes on the inputs together, and these three spikes will be enough to cross the threshold. So they will emit a spike. Okay, and a different neuron will get like it gets. So not every neuron gets input from all these fibers. Okay, so if you take another neuron that happens to be like receiving the input from this one, that one, and that one, it will get the three spikes of the blue ones together, and it will code the. It will spike only when this blue stimulus will be given. So now what you can see is that basically what we did is that we based on this latency code that is consistent between the receptors, we transform it after this stage into a code which is a special code. Okay, so it's like labeled line. Whenever this neuron is actually spiking, we know that the input was red, and whenever this neuron is spiking, we know that the input was blue. Okay, and now it's not so much dependent on the latency anymore, but the information was not actually carried out by the frequency of the input, but by the timing of the input. And you can actually continue to rely on the timing, because, it could be that there would be like few neurons here that are red that would spike at the same time when the red stimulus will be given, and few neurons that are blue which will spike at the same time when the blue things are given, or even if they're not spiking at the same time, just by the convergence at the next level, you can also extract different kind of information about the original stimulus. So the idea here is using the time of the spikes, even though everything looks like very jittery, to extract information out of the system. Yes?
But how in the end you can separate between the red and the blue? Because it seems that you have both stimulus in one receptor and
No, but here, now there are different neurons. So say now I'm looking at the axon that's coming out from this nucleus. Okay? So when this neuron is spiking, I know that it was a red one, and when this neuron is spiking, I know it's a blue one.
this is one step.
Afterwards,
Oh, before.
here.
You have both like the one in the end, the blue one in the end. You have blue, and after it you have red. And no.
Yeah, here. Yeah, but only this. So look, this neuron is receiving this input, that input, that input, and that input. It gets like 4 type of inputs. Okay. Now the reds are also arriving, but they would not arrive at the same time. So this red would arrive first, then this red would arrive, and then this red, and then that one. So they would go like 1, 2, 3, 4. You never reach threshold. On the other hand, the blues are getting 1, 2, 3 together, and then later comes another one. So the another one doesn't do anything, but the 3 that comes together can summate in order to cross threshold.
How do you produce this initial flight of corrections?
It's a good question. I don't know. That's a good question, which is something to do. Um, I mean, in their case, it's basically an experimental. It's experimental observation. But yes, it could be that these ones are all touching the receptor at the same time because it's flat, and this one because it's convex, and the thing pushes through into your hand. So the first one, the one on the top, will activate first, and the others will activate a little
But
bit
they're
later.
both in the same capillary, right?
Yes, but it makes sense that they will activate it in a different time. Also, when you apply the pressure in different directions, right?
And would it mean that somatosensory has the same components, maybe like a visual system, lines and dots and circles, that from that it express the information?
I think I told you it last time. So the one of the issues here is that it could be, yeah, but it's a little bit difficult to know in the sense that we'll talk a little bit about it in a second. But it's a little bit difficult to say because it's a sense, I think, that we have much less introspection into, right? It's like it's difficult for us to actually we use this sense, but it's difficult for us to access in a way the very basic elements, which I think in vision it's a little bit easier. But it's true also in other senses as well. I mean, in olfaction, for example, you have the same problem. But you don't really have an access to what you actually perceive as the basic elements. But it's it makes sense that when you and I'll show you some examples that you're sensitive to gratings, to special frequencies. Okay, texture is in a way, at least at a very basic level, is special frequencies. Like, what's the distance between lines if you just make a mesh? Okay, what's the difference between the special distance between the line? Is similar to special frequency in vision in many senses. Yes.
Why is it more difficult to test it than in vision? Because in vision you don't really need, and the problem with the layout curve, it wasn't based on introspection, it was based on...
No. I mean, okay. So it's not more difficult to. It's not more difficult to test. It's more difficult to kind of plan what exactly is the stimulus that you're going to test. In a way, you will envisage was a chance, right? They didn't actually look for lines. They found it by mistake. So mean they emphasize it. Of course, it's never either or. But in this case, they emphasize the fact that if you synchronize the inputs, it's easier to drive the neuron, or you need less inputs to drive it.
But why is the function of the latency of the first spike? It's function of the exact localization of each spike in your
because
brain. So
it's true. I mean, it's again they emphasize it because that's the way they do the experiment. But as we talked a little bit before, touch is an active sense, so you can kind of imagine that you do that, right? And you look at the texture, and at different locations there will be like synchronization of different receptors because they're hitting something on the texture at the same time, and this will give you some information about the special frequency of the texture, right? So imagine that you move your hand over I don't know, something that is made of something that has some frequencies like that. So you get like activation of the inputs at different times, but together. All the receptors on your hand at a certain place will be activated together every time you hit the reach, right? And this is a way to kind of convert. If you move your hand at a constant time, it's a way to convert the special frequency into temporal frequency. And if you rely on the timing, you can actually extract some information from that. Okay. Okay. So cortex. So in the way this thalamus, why is it? I completely skipped it. There was a slide that says thalamus. Skip it. Okay. And we're going into cortex. So somatosensory cortex, we said, is very close to the motor area. So there's a central sulcus that would be the motor, the M1, the primary motor area, and the somatosensory area itself is so the primary somatosensory area is divided into several sub-regions, 3, 1, and 2. It's a bit kind of complicated to know why they did it like that, but okay. So this is the primary motor cortex. Okay, and here starts the somatosensory area inside basically the sulcus, right? It's like the cortex is folded in, and this is one area, and this is another 3B, and this is 1, and this is 2. And from here, you're starting basically 2 already is already starting to be part of the secondary somatosensory area. And primary somatosensory area is in many ways similar to things that you've seen before. For example, in visual system, and in the sense that information is coming from the thalamus to layer 4 of the somatosensory area, but different. So the thalamus itself has different subnuclei, different than visual system where you have LGN. Here you have several nuclei in the thalamus. The main one is VPM or VPL. In human, it's called VPL. In rodents, it's mainly VPM. There are others that also transmit information. Information comes to 3A and to 3. So each one of these areas, 3A, 3B, 1, and 2, is getting direct information from the thalamus, but also there is flow of information lateral inside the somatosensory area from 3A to 3B and from 3B to 1. They're all kind of converging into 2, and then this would be the higher areas like V2, V4, and other visual areas in kind of similar idea. One thing that I wanted to mention is that in fact the idea of cortical columns that you probably have heard of when we talked about vision actually started by in the somatosensory area with Mountcastle, and Mountcastle was a famous electrophysiologist that was actually studying in monkeys, studied somatosensation. And one of the things that he found is that, so what you see here is like penetrations of an electrode through the cortex. And he was studying, if you remember from the first, from our first talk, there was one of the receptors was called the Pacinian corpuscle. Anyone remember what's special about that? It looked a little bit like an onion. So the Pacinian corpuscle was the one that is deep in the skin and is conveying fast frequencies, up to 200 hertz. Okay, so if you stimulate, if you make some vibration on the skin, very, very fast vibration, the only receptor that is responding to that is the Pacinian corpuscle. And this gave him a good access to separate different modalities. So if you give stimulation, say, at 4 hertz or at 200 hertz, you know that you're activating at the same location, you're activating different receptors. Okay, and what he found out that when he's doing penetration along inside the cortex, deep in the cortex, perpendicular to the cortex, to the surface, it keeps kind of receiving information from the same modality. Okay, but when they move around, they're starting getting information from different modalities. And also when you see that the cortex, you remember that the cortex is folding in. So if you now go here perpendicular to the skull in that sense, because to the cortex would be like that. But if you go like that, then it means that you go through different columns, if you like. Okay, and then the type of modality is changing with the depth of the penetration. So the idea of a cortical column, the idea that an area in the cortex is dedicated to the same type of information, started with Mountcastle, then Hubel and Wiesel saw it in the visual system in maybe a more convincing way, but it started here. These are details. So like each one of these areas is responsible for different type of receptors, and again in a columnar organization. It's not as it's somatosensory somatotopy, as we said, mapped similar to the visual system, and then inside each one of the areas, it's also subdivided into different type of receptors. So what kind of receptive fields? So I don't need to introduce you to the concept of receptive field anymore, right? So we're talking about what type of responses you would get from a cortical neuron in primary somatosensory areas, and there are kind of different type of receptive field, and these are spatial temporal receptive fields. So they're also both in space and time. So you can see that you can activate a neuron from a localized area in the on the figure. So this would be an excitation-only receptive field. So if you touch it here, then the neuron will get excited and maybe will get more excited with time, and it will with time will go and disappear. But there are also neurons that has like what we call the replacing inhibition. So you will stimulate them, they will be excited, but afterwards, if you try to stimulate them, they will be inhibited. And there's also surround inhibition or surround replacing inhibition. So first they will be excited, but then the inhibition will take over. Okay, so this is in a way similar, not so much to visual somatosensory neurons, to visual neurons, receptive fields, but more, if you like, to thalamic receptive fields, which is on-off, with on-center, off-surround type of receptive fields. This is what you would get in primary somatosensory area. I don't think this is relevant. Okay, and then if you go to higher areas, you will start you will see more complicated receptive fields. So this is an example where you have a what you do, you put some grid on the finger and you test for both orientation, okay, and intensity. So how strong you push towards the finger, and also you test intensity and location. So this is central location, and then you move it to different areas, like relative to the center, okay, and then you can also twist it around. Yes.
Are there also off-center receptor fields, or are those?
I don't know of off-center, okay, but they might be. Okay, so the idea here is that you will have like you have like two dimensions, okay, and you can see that it's not uniformly distributed around each one of the dimension. So you have both preference to some orientation, and you also have some preference into location. Okay, so the neuron actually prefers this orientation and this location, and say this orientation at that location, and it's actually inhibited by this orientation at this location. Okay, so you have a complicated receptive field, which actually kind of completely reasonable with what we kind of think of cortex in any other aspect. Of course, each one of them has also temporal dimension, so I'm not going to go into that. It's a little bit too complicated for now. And let's take a break, and then we'll start with barrel cortex for the last hour.
אפשר לשלוח את זה? כמו פעם שעברה? אני לא ראיתי את זה אונליין. פעם שעברה?
כן, אני שם את זה שם.
או איך זה קוראים? פעם שעברה, או ששלחת לי את זה, או ששמת לי
שמנו את זה במודל, לא?
האם אתה יכול?
אם יש לך, בוא תביא.
כן, אני אביא את זה.
אני לא שם את זה, מה?
למה? שלח את זה רק לדן?
לא, אז דן שולח לכם בוואטסאפ, אתם לא רוצה לשבת אצלו.
לא, תשים במודל.
אני גם רוצה לבדוק.
מה? למה לא?
כי פעם שעברה אני שמתי את זה בדרובוס לכולם. אני העתקתי את זה.
אז לא, חבל לפתח את הדרובוס.
בסדר גמור.
best model.
הדבקתי את זה למעלה, מצלם כזה עם מוזיקה.
אני רק יכול לחשוב עכשיו מה הדימוי שקראתי. אני נהניתי. נראה לי שזה היה מסודר. למה? לטילה לא עליי. זה היה תגובה מאוחר מדי, אבל מה שזה יכול להיות המחקר.
נפגשתם גם ברוסקות?
מה?
נפגשתם גם ברוסקות? כן.
כן, חבל ש...
גליל קומדי אופן.
בג'ל כזה, כמו
אוקיי.
כמו לשיניים, זה מכיל בעצם TTX, זה משתק צדדים שונים, ואז אתה לא יכול להרגיש כאב. בקיצור, זה חומר משיכת כאבים, לוקאלי, בעצם עם סיכה מאוד דקה, ניסינו אותו לתוך הראש.
מה זה לתוך הראש? יודעים איפה העצבים בדיוק?
כן, אתה יודע איפה העצב, אני לא יודע, אני לא עשיתי את זה, אבל אתה יודע איפה העצב, אתה נכנס הביתה.
אוקיי, ואז איך ההפרדה הזאת, אתה נכנס לבנדל של מיליון עצבים, איך ההפרדה הזאת אחר כך הוא הספציפי שבקצה יש לו והוא שלידו והוא שלידו והוא שלידו?
כי מה שאתה עושה, אתה מחבר את זה לאמפליפייר, אתה מודד ספייקים, ואז אתה הולך ולוקח עם סיכה ונותן איפה אתה מגיע. אז נניח אתה מנופל למקום הזה, אז אתה נותן סנטיב כאלה או נותן גירוי ארוך, ורואים מופס אדפטיב או סלו אדפטיב. אבל אתה יכול להפריד בגלל שהמחט שלך היא מאוד מאוד דקה, אתה יכול למדוד רק משניים שלושה ספייקים.
אבל אתה רושם עם מיליון
לא, אתה יכול להפריד, אתה עושה מה שאנחנו קוראים ספייק סורטינג. אתה מקבל הרבה ספייקים, אבל כל אחד מהם, בגלל שהאלקטרודה שלך לא נמצאת בדיוק באותו מרחק מכל אחד מהאקסונים, אז כל אחד מהספייקים נראה טיפה אחרת.
אתה אומר שאתה מכניס פה סיכה למיליון אקסונים ואתה עוד רושם רק
חמישה.
עכשיו?
זה אותו דבר כמו שאני עושה במוח, גם במוח אני מכניס אלקטרודה, ואני מודד יש שם 100,000 נוירונים.
כי זה כדי ליצור את הדבר הזה של ה-time separation הזה, נכון?
אתה צריך לעשות, אתה צריך להיות מסוגל להפריד בין אקסונים שונים. ואתה לא יכול לעשות את זה ב-100% במובן הזה שאנחנו לא יכולים להיכנס לאקסון אחד ולמדוד רק ממנו. אתה צריך לסמוך על זה שהספייקים של אקסונים שונים יודעים שונים.
אוקיי, עכשיו בקטע עם הפלט והכדורים. אז כאילו הזמן מאפס תגובה עד תגובה מלאה באינטנסיטי מלאה היה אותו זמן בשני המקרים? זה דבר ש... אני מנסה לחשוב איך אתה מסביר את ה-time lag הזה בהתחלה. אוקיי, אם אתה שם את האצבע משהו פלט, יש לך איזשהו פרק זמן, אני שם אותו על האינטנסיטי הסופי אותו אינטנסיטי סופי, הטוטל זמן מ-0 עד 100% אותו זמן, אבל יש לך איזשהו time אחר.
אז בוא נסתכל נניח על העובדה שכשזה פלט, אני נוגע כאן, אז כאן כל הרצפטורים שנמצאים על קצה האצבע יפעלו פחות או יותר באותו זמן. וכאן, אלה שנמצאים ממש על הקצה, יפעלו ראשונים, ואלה שנמצאים יותר רחוק מהריץ' הם יפעלו קצת אחר כך.
בוא נגיד, אם הייתי עושה טיפה יותר מהר, אז זה הגול, מאשר לפלט, הייתי כאילו מביא את זה
יכול להיות שזה גם יכול לשנות.
הייתי מביא מישהו יכול על השני.
אולי, יכול להיות. זה יכול להיות די מסובך לעשות את זה בדיוק אותו דבר. העניין הוא, אני חושב על זה ככה, אני חושב על זה שיש איזה, יש כאן, יש שתי גישות לעניין הזה. גישה אחת, אני לא יודע אם היית פה בהרצאה של, אנחנו עכשיו הולכים לדבר על הוויסקר, אבל אני לא יודע אם היית פה בהרצאה, הייתה לפני איזה כמה שבועות, באחד ההרצאות ב-50, הרצאה של מישהו בשם דוד גולד, והוא עשה את כל הפיזיקה של איך הוויסקר מתכופף כשמפעילים עליו כוח. היית בזה? היה לו שם משוואות דיפרנציאליות מטורפות, כאילו, כדי לראות איך הוויסקר הזה מתכופף. זה דרך אחת ללכת, ואתה יכול להגיד, טוב, יש לי אור, זה איזשהו חומר אלסטי, בוא נקרב אותו כמו איזשהו חומר ומה תהיה הדפורמציה כשאני שם, ובוא נניח שיש משטח אחיד של רצפטורים שהם מתפלגים בצורה אחידה בין Global Adaptive 1 ו-2, ועכשיו אני אלך ואני אגע בזה עם משטח ישר ועם משטח עגול, ואני אעשה איזושהי משוואה ואני אגיד כאילו מה יהיה הפרשי הזמנים. זה דרך אחת לעשות את זה.
הרבה לפני, אתה מסתכל על נוירון, מה שאתה רושם פה זה ספייק מאיזשהו נוירון בודד, הצלחת לבודד את הספייק מנוירון בודד. אז מה אכפת לך בכלל אם המשטח הוא עגול או פלט? אכפת לך בסוף רק מהאינטנסיטי על איזושהי נקודה ספציפית? זה לא שאם אתה רושם נוירון בודד הוא לא יודע אם זה פלט או זה עגול.
אחד מהם לא יודע.
אבל מה שהראית לנו זה כאילו שומעים מאיזשהו אחד ספציפי כל פעם, ואיך מגיעים בעגול וזה פלט.
כן, אבל לא. תחשוב שזאת האצבע, יש לי רצפטור פה, רצפטור פה ורצפטור פה. ועכשיו אני מתקרב לזה עם פעם אחת עם משהו כזה ופעם אחת עם משהו כזה. ואני דוחף אותם. אז כשאני אדחוף עם הדבר הזה, אז הוא יפעל ראשון, אוקיי? ואחר כך זה יפעל אחר כך וזה יפעל אחר כך. וכשאני אעבור עם זה, אז הוא יפעל ראשון, אבל עד שזה יפעל ייקח יותר זמן מאשר במקרה הזה, ולכן יהיה דיפרנס בלייטנסי. זה הכל. זה כל מה שיש שם. עכשיו השאלה מה אתה עושה עם זה. ואמרתי, דרך אחת זה כאילו ללכת ולעשות מודל, כאילו יש לי משטח עם משהו אחיד וזה, איך אני יוצא ממנו עם האינפורמציה. ודרך השנייה זה להגיד, יש כאן מספיק וריאביליות. כי הרי אף פעם אני לא צריך, כי האצבע הזאת שונה מהאצבע הזאת והאצבע הזאת שונה מהאצבע הזאת. כל מה שאני רוצה לדעת זה שיש כאן מספיק, האם יש כאן מספיק וריאביליות כדי להוציא סוג האינפורמציה שאני רוצה. אוקיי? בעצם שתי השאלות לא נענו. זאת אומרת, אנחנו לא יודעים, אף אחד לא עשה לא את זה ולא את זה. אוקיי, הדבר שהראיתי לכם זה פחות או יותר הכי קרוב לזה של להראות שיש מספיק וריאביליות כדי להוציא כל מיני סוגים של אינפורמציה. זה חייב להיות בגלל שעובדה היא שאתה יכול להוציא הרבה סוגים של אינפורמציה, ויש גם הרבה אינפורמציה שאתה לא יכול להוציא. זאת אומרת, זה גם הרגישות של מה אתה יכול לעשות.
כן, אבל זה הבסיס לטיים
אני חושב שזה. ככה אני מפורש את זה, אני לא רואה הרבה אפשרויות לראות את זה. יש כאן את העניינים האלה, שמעתי לך, יש כאן גם, אמרתי לכם את זה פעם קודמת, האור הוא גמיש, אז כשאתה לוחץ על הנקודה הזאת, אז זה גם מגיב לזה.
כן, זה אם תתפוס את המשטח הזה למעלה ממש מהר.
בבת אחת, אתה יכול לגרום לסינכרוניזציה של כולם אפילו ביחד. אני בטוח
בזה. אני כל כך זניח,
אבל זה ברור שכשאתה תעשה ככה ותעשה ככה, כאילו אם תעשה את זה מאוד מהר, אתה לא תוכל להגיד להסביר.
אבל עדיין גם בלי קשר, יש קשר בין פריקוונסי
כמו שאני עושה לך כאילו, אתה יודע, אני לא חושב שאתה כמו שם פריטבלים, ואז אני עושה לך אותם בעוצמה מאוד חזקה ולזמן מאוד קצר, ואתה לא תוכל להפריד ביניהם, אתה צריך איזשהו, אתה צריך משהו כדי להוציא את האינפורמציה, אתה לא נותן לי את זה, אז אני לא עושה.
אבל עדיין רק יש קשר בין האינטנסיטי של הגירוי לפריקוונסי.
יש קשר בין האינטנסיטי לפריקוונסי, ויש גם קשר בין האינטנסיטי ללייטנסי. גם ככל שהמפריעות יותר חזק, אז אתה תקבל את זה יותר מהר.
הבנתי את הסלייד האחרון, האחד לפני האחרון. כן. יכול להסביר לי שוב מה הניסוי ומה המשמעות של זה?
אז הניסוי זה שיש לך גריד כזה של פסים שאתה שם על האצבע. הרעיון הוא כאילו עכשיו לעלות רמה ברמת הגירוי. עד עכשיו הגענו תמיד עם איזושהי נסיקה. עכשיו אנחנו נוגעים עם משהו יותר מסובך. אז אתה נוגע עם משטח שיש לו איזשהו גריד כזה, אוקיי? בזווית מסוימת, ואתה יכול לשנות את הזווית שבה אתה נוגע. ואתה גם יכול להזיז את המרכז של איפה שאתה נוגע. זאת אומרת, אתה יכול לגעת ככה, בוא נשים את זה ככה. אתה יכול לגעת ככה, 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 ככה וככה. זה מה שאנחנו עושים כשאנחנו עוברים מהשורה הזאת לשורה הזאת. ובכל אחד מהם אתה יכול גם לגעת בכל אחד מהזוויות. אז נוצרת לך מטריצה של כמה אתה אופסט מהמרכז של האצבע וכמה אתה בזווית. והנוירונים, אתה מודד לך מנוירון ב-H2, זאת אומרת, זה כבר לא בסומטוסנסורי אחד, לא, זה נוירון אחד. כל אחד זה נוירון אחד, כל הדבר הזה, כל נקודה זה ספייק, ונוירון אחד, וכל שורה זה טרייל אחר. אני צריך לחזור על זה אם אתם לא יודעים. לא, בסדר, ואז אתה אומר, הנוירון הזה למשל, אתה רואה שהוא יורה הרבה ספייקים לגירוי הזה, כשהדבר הזה נמצא גבוה על האצבע.
זה אינדיקציה לאיפה נמצא המרכז?
כן. אוקיי, וככל שאני מוריד אותו, הוא עדיין מגיב, אבל הוא מגיב פחות כשאני בצד הזה מאשר בצד הזה. אוקיי? עכשיו אני לוקח את זה ואני מסובב את זה קצת. אז דווקא במקום הזה הוא לא מגיב כל כך הרבה, אבל כשאני יורד הוא מגיב יותר. ואז כאן הוא מגיב, שוב, כאן יותר, ואז באיזשהו מקום הוא בכלל, אם אני שם את זה ככה, במרכז, הוא בכלל באיניביציה, הוא לא יורה בכלל. אז יש לו כאילו עכשיו כמה פרמטרים שהוא משחק איתם, גם איפה זה נמצא וגם זה. עכשיו, באופן כללי, אתה יודע, יובל וויזל היו אומרים שזה נוירון שמגיב לאוריינטציה במיקום מסוים בעולם, אבל זה מאוד מלאכותי בגלל שאתה יודע, אתה יכול לשנות את סוג הגירוי עכשיו במקום לפסים, לנקודות, וזה משהו שעושה כאילו, אני לא יודע, משהו אחר. הוא גם יעשה איזה מין תבנית כזאת, אז זה קצת קשה להגיד בדיוק למה הוא מעדיף.
יש לי עוד שאלה. אז הריב, קטע בין שתי רזולוציות, התחלתי הראית שאתה on center הזה, נכון? אז יש לך זה, ואז אינהיביציה מבחוץ, אבל גם בהתחלה הראית לפני זה, הראית שאם אתם רוצים לראות אחד, אתם רוצים מהקטע שליד. לא? מהקטע שליד. ואז אמרת, אם נסתכל עליו, אתה יכול להגיד הוא מהפה, פה.
נכון.
אחרי זה, אתה אומר, יש לנו את ה-on center כדי ליצור מקום
לא, כי זה עובר גם בדיוק בגלל ה-convergence וה-divergence. תראה, אם יש לי 3 רצפטורים, אז אני מפעיל כאן או כאן, אני לא יכול לדעת מי מהם מפעיל אותי.
זה באור.
נכון? זה נניח באור, אוקיי? אבל נניח עכשיו שיש לי עוד נוירון, שהוא ירוק, והוא עושה את זה. עכשיו יש לי נוירון כאן שמקבל משניהם.
זה עושה חיתוך של
בדיוק, זה עושה חיתוך. אז כל הזמן זה עושה חיתוך בייחוד, בכל שלב זה עושה חיתוכים בייחודים כאלה.
אז מה שראית את ה-on center זה מן סתם ברמה הרבה.
זה כבר בקורטקס, וזה כבר עבר איזה 3-4 תחנות כזה. אני לא רוצה לקרוא להם.
רציתי לשאול לגבי התכונה הקודמת, עוד סבבה, התכונה ששאלתי אותך לגבי הרצפטורים עגול עם הגירוי העגול והמרובע. כן, אז אני מבינה את מה שאתה אומר, שלפי הזמן שאתה מגיע כנראה זה עובר קצר. אבל אם יש לי באותו נוירון שני הרצפטורים, וגם בגול וגם באדום, אז איך הוא יודע מה בסוף מגיע לה? למרות שהפולס של השלושה כחולים יהיו ביחד, אבל איך הוא יודע
הרצפטורים הם אותם רצפטורים, הם לא כפולים באדום, זה אותם רצפטורים. אבל הספייק שמגיע מהגירוי האדום מגיע לפני הספייק שמגיע מהגירוי הכחול. פשוט בגלל שהאצבע נראית ככה. וכשאני שם גירוי שטוח, אלה יוקרנו קודם, אבל כשאני מגיע לכם, אז עד שיגיע לכאן, עד שיגיע לכאן, ככה זה לא יש זמנים שבהם כל אחד מהגירויים האלה, כל אחד מהגירויים אני נראה שזה פעם לזה או פעם לזה. טוב. Okay, רק עוד הערה אחת לפני שממשיכים. Just one note before. I just wanted to make sure that you understand what I showed on this figure. And what we show here is this grid is placed on different places along the finger and with different orientation. And each line here is a repetition of the same experiment, one after the other. So these are raster plots, and this is time. Okay, so every dot here is a spike, and every line is one trial. So I put the grid in one orientation at a certain position, and I record the spike, and then do it again, and then do it again, and then do it again, and I get all these responses, and I compare now these responses to say these responses, and I can say that when the grid is in this orientation at this offset, like 3 millimeters off the center of the finger, the neuron is excited, but when it's in this orientation and it's on 0, it is very inhibited. Okay, just to make sure. Okay, so now זה לא עבד עם המודל. Okay, so this was a brief overview of what happens in higher areas, and now I'm going to, so these days when people are talking, this was very typical type of experiment that people have done, say, I think something like up to, say, 10-15 years ago in monkeys, a little bit in rats, and today when people say that they're working on somatic
95% that actually means the barrel cortex. Okay, so the barrel cortex is an area that we're going to talk about in more detail now. It's part of the somatosensory system of rodents, and it's a model system. So you should take it in the right mind, in the sense that it is a somatosensory system in a mammal, but it doesn't exist in humans. So our ability to extract information about it is you have to remember that in the back of your mind when you talk about it. Okay, so what is special about barrel cortex? So we start with the whisker system. So rodents, not only rodents, many animals, seals and cats and dogs, many animals have whiskers. They're using it for different purposes. Rodents use it as one of the main source of information because they are living usually in the dark. They don't see so well, and they mainly rely on olfaction and on somatosensation in the sense of the whisker system. So I'll show you some details about it. So the whisker system of rodents is very, very stereotypical, so much so that we can actually look at a mouse or a rat and say, this is whisker A1, and this is A4, and this is E1, and this is alpha, beta, gamma, and delta. So it's very easy. You look at it from the side with even with the naked eye, and you can identify which whisker comes where. And these whiskers are usually move, so the animals are moving them actively. I'll show you in a second. They can move them in every direction, but mostly they move it forward and backward. And there are certain things that they can certainly do even with one whisker. For example, they can discriminate between two textures. You can give them like sandpaper number 1 and sandpaper number 5, and teach them to say whether it's this one or that one. That's one of the things that they can do, and they can do it with one whisker only. Another task that is famous is gap crossing. You can put them on a platform in the dark, and they need to jump to the next platform in order to get a reward. And you change the distance between these platforms, and the only way they can, because they cannot see it, and they cannot smell it, the only way they can tell whether the platform is too far or not is by leaning forward and try to touch it with the whisker. And if they touch it, then they know that they can actually jump, and they jump to the next platform. So here are some examples. Over the last, 15 years or less even, people started taking high-speed videos of rats and mice, and you can do it in complete darkness. And what you can see here is a rat on a platform in front of actually a wall which is made of glass, and it cannot see anything. And I want to show you these two movies. So this is by a guy called Tony Prescott in Sheffield in Britain. And the point in this movie is to show you the following, that more or less until his work, people usually thought that mice, rats are moving the whiskers very stereotypically. So the idea was that there was what they call central pattern generator that would actually move the whiskers at 5 or 10 or 8 cycles per second. And this is how the animals are using the whiskers. But when you look at them in this way, so the idea here is that there is a corner, okay? And apparently the animals are very sensitive, and they don't like the whiskers to be bumped into things unexpectedly, and they want to keep, it's important for them to keep them, so they protect them by retracting the whiskers if they know that they're going to hit something. So if you see what the rat is doing here, it's whisking, all right? You see it's going forward and backward, but at the point where it touches the wall, one of the whiskers is touching the wall, it retracts all the whiskers on one side, but it actually continues with the other side. So they can actually control at least the two sides independently. Sorry, just show you again. Okay, watch it when this one touches. You see, it touches it. Take these ones back, but it continues with this one. Okay, this is another example. So now it walks on a platform which is transparent, and it's in the dark, so it doesn't know if it can actually move forward without falling, because it could be an edge. Okay, so what it does, if you'll see it here, it touches with the whiskers on the floor, and it's kind of like a blind man using a stick. It touches on the floor to see if he can actually go for it. And the other thing that you can see here is that when the whiskers are touching the wall, it kind of stops because it understands that it's going to bump into something, and it's very, very accurate. From the few touches of the whiskers, it knows exactly what to stop. Okay, so it kind of extracts the information exactly where the wall is just by the few touches of the whisker, and it needs like one touch to know that. It doesn't need to do like hundreds of touches to do that. So it's a very, they know to extract a lot of information out of this system. And recently, one of the papers that will be presented in the next meeting would be also on how they're using these whiskers for social interaction. Okay, so this is something that is becoming more popular recently as well. Okay, that's another example. And what you see here is now, this is not a rat, this is called the shrew. The shrew is a chadaf, and it's a chadaf, it's the smallest mammals that exist. And these are almost completely blind. They don't see anything. They mostly use the olfaction and smell. And there are predators that are actually eating all kinds of cockroaches and things like that. And from experimental point of view, some people thought that it would be interesting to study them because the brain is so small that you could at least ideally image the whole brain at once. Okay, which is something that in mice we won't be able to do in the near future. And this is one of the things that they do. So the idea was to study that. So here it's difficult to see. I don't know if you can see I can put you the link to the movie, but what happened actually here, sorry, is that once the cockroach antenna is touching the whisker, it's enough for it to know that it's going to, where it is actually, and to make the attack. Okay? Okay, so, yes.
I have to remember, what do you mean by image from the whole brain at once? With this technique using...
Two photon imaging. So the whole brain is small enough that you can do you can image every point on the brain.
But not all depths at the same time.
Not at the same time, but I don't know if you've seen it, but this is really kind of last year people have demonstrated that there are animals like in electric fish, they can actually image all the neurons at a single neuron resolution. So you know each neuron when it spikes for the whole neurons in the brain in a fish. So if you want to ever to do it in a mammal, probably mice is impossible. The brain is too big. These ones are just on the edge of it. It's 2 millimeters, I think, the whole brain, if I'm not mistaken. The person who worked on that is Michael Brecht. I don't know if you know him. He'll be on the last slide of this presentation. Okay, so the whisker itself is like a hair. It's a dead tissue, so there is no receptors on the whisker itself. All the reception is done inside what's called the follicle. So a follicle is a kind of a sac that is made of so there's skin here and there's a muscle here, and actually these are the fibers that innervate the muscle and allow the movement of the whisker. But the base of the whisker is wrapped with many, many types of receptors. One of them is a Merkel ending, which is one of the receptors that we talked about in the skin. There are also kind of other free nerve endings and others that are not completely identified yet. And all these fibers, all these receptors are actually sending axons through outside the follicle, and this axon is the axon that conveys the information that comes. It's nerve, not this axon. It's axons in a bundle. These are conveying the information from the whisker to the brain. Okay, so what is special about this system? First of all, it's a very short path from the whisker to the cortex. It goes from the whisker. There's an axon going through a dorsal root ganglia. Inside, what does that look like?
Brainstem.
There's a brainstem, exactly. So in the brainstem, there's a ganglion called the trigeminal ganglion. The axons are making synapses of neurons. These neurons are sending the axon to the thalamus, and from the thalamus are sending it to the cortex. So it's 3 synapses all the way from the whiskers to the thalamus, to the cortex. Okay, now the cortex itself, first of all, you can see that this is a huge part of cortex. So in rodents, the somatosensory area that is devoted to the bowel cortex, so to the whisker system, is as large as the rest of the somatosensory area. So it's a huge area, which also means that a lot of the information that the animals rely on is coming from the whisker. Okay, but what is special about it? It's special because if you cut the cortex in a certain way and you stain it, and this was first done in the 70s, it's really difficult to see.
Stain for what?
So this is some kind of staining. I don't even remember. It doesn't really matter. It's just a reaction. It's not like something very specific. But you can do it today in a much more specific way. What you see is that there is an organization on the cortex that is a complete reflection of the whisker pad. So each one of these areas, these brown areas, correspond to one of the whiskers. And if you look at it in a 3D manner, so if you slice it one on top of the other and kind of draw these brown areas, they look a little bit like a barrel, like a chavit. Okay, so this is kind of as if the cortex is like a wine cellar containing barrels that are stuck next to each other, and so this is called the barrel cortex. So what does it actually mean functionally? So the first thing I want to show you is that this organization is so robust that today you can actually identify where a specific area, like where a specific barrel is in the cortex, without even opening the skull. You can look through the skull. If you put water on the skull, it becomes the bone is thin enough in mice to become transparent, and then you can see the blood vessels underneath the skull and the cortex, on the cortex. And if you then move one of the whiskers in a high frequency, and you image the brain with illuminated with a red light, you basically get something similar to an MRI, because the area that is now excited in the cortex would consume a lot of oxygen, and this will change the reflection of the red light. And if you analyze this picture, you can actually have a high spot or a low spot of activity, and this will give you the location of the barrel that correspond to the whiskers that you moved. And just to make sure that you kind of on the right location, you can actually then move to a different whisker, and the spot moves inside the frame. So this actually tells you that you are above a certain barrel, and then you can even put an electrode there just to make sure if you want that you are right. some labs, this is a lab in France of Daniel Schultz. All of you have been in Veggie, right? So you remember the talk of Daniel Schultz. What he was doing, he made of these, so these things that I showed you here. This is called a piezoelectric device. It's a small ceramic element that if you apply voltage to it, moves, and you can actually move the whisker in a very, very precise manner. So he built a matrix of 24 of these, and each one of them has two piezos, so it can move in both directions. And then they can actually stimulate each one of the whiskers separately and all the whiskers in a certain pattern, and you can actually get a map of, say, one neuron. Okay, you can actually map the receptive field activated from all the whiskers. Okay, so for example, this neuron is activated mostly by C2 neurons, but also by B2 and also by C3 and C1 and B1. So it has some kind of a wider receptive field. What does it actually mean, these black spots or brown spots that we saw on the cortex? What actually we know today is that the axons that are coming from the thalamus are concentrated to certain areas in layer 4 of the cortex, and these areas are separated by other areas called septals. So all the axons that are coming, say, from the C2 whisker, they're coming to layer 4, but they're not getting, not to here, and certainly not to the boundaries between them. And thus all the information that's coming from that whisker is coming to this area in layer 4. However, the cortex is actually built in different layers, and this is a topic to a whole different talk that I think you should at some point get, but maybe today is not the time to do that. But this is today the model system to study the anatomy of a certain, how the cortex is actually wired up. And people have done it by, for example, doing the following, now intracellular recordings from a neuron in vivo, moving the whisker and recording responses. We'll talk about it in a second. But then afterwards, reconstructing the cell. So you put a dye in the cell, and after that you can reconstruct the cell in a very, very high resolution, and you get a three-dimensional representation of the neuron. And then you can put together one on top of the other all the neurons, and then you can get like an estimation how the anatomy of this area in cortex looks like. And the one thing that you can see is that the dendrites are concentrated in. So this is layer 4 where the axons comes in. Also, the dendrites of layers 2, 3 pyramidal neurons are also concentrated in this area, but they're also sending dendrites and axons to other barrels. So this could explain, for example, this response that we saw here, that the neuron in C2 barrel are actually excited also by a different whisker. So for example, you can do the same experiment, but now looking at the subthreshold potential of the neuron. So you see that you give a stimulation, you move whisker C2, so now it doesn't move, then you jump to some value, it means you move the whisker, and you wait for a while, and then you move back, and you see that there's an excitation response to the whisker movement, and then another one at the end, and this is subthreshold, okay, and some of them will be suprathreshold, and you can do that for different whiskers, okay, different rows and different whiskers, and you get the map, the receptive field in terms of subthreshold activation of the neuron, and here it's more widespread than you see in this experiment, because here, even if you have an EPSP from this whisker, you don't see it because you only record some. So this is the basics of how the barrel cortex is organized, and as I said, this is becoming today the model system to study cortical organization. People are talking about a hot topic, one of the most hot topics today in neuroscience is cortical circuits. What type of neurons they are, how they are talking to each other, how this interaction is creating function, and so people identify different types of neurons. These are the famous layer 5 6 tufted pyramidal neurons. These are the layer 5A layer thin tufted pyramidal neurons. These are the layer 4 spiny stellate cells. These are layer 6 neurons. And what they try to do is actually combine them into what they call the digital column. So they kind of say, okay, we have certain amount of this type, certain amount of that type. This is the morphology of each one of them. Can we actually put them together and make a reconstruction of the whole cortical column or the whole barrel cortex? And two of the efforts that are done, the leading efforts, there are few directions. People are using different techniques, but two of the main efforts are done in collaboration with people here. One is Chaim Sampolinsky is involved in one of these with Bert Sackman, which is using one type of direction, and another one is Idan Segev, who's working with Henry Malcolm, who's trying to do it in a different way. Okay, so they're both trying to reconstruct the column, and assuming that the column is some kind of, maybe I haven't said that, but you understand already that a barrel cortex is actually organized in the extreme example of cortical columns that we talked about before with Mountcastle or Hubel and Wiesel, because when you take the cat's brain and you look at the cortical column, morphologically, they all look the same. You can actually tell without measuring, just by the anatomy, you cannot tell that you move from one column to another column. In the barrel cortex, you have the septum, so it's very clear. This is one column, this is a different column. You know which neuron belongs to which column. Some people think that this is obviously a good advantage. We can now study a whole cortical column in separation. Other people say this is such an extreme example that it actually might not be relevant to say visual cortex because it's very, very different in the way it is organized. But in any case, it's a very clean way to know what neuron belongs to which barrel. Okay, so one of the things that barrel cortex is famous for is the fact that it's relatively easy to show experience-dependent plasticity.
Sorry, quick questions. What is the material that the septum is made from, and do all these modeling approaches completely ignore glia cells? So they look at neurons only?
Yes, they completely ignore glia cells.
Cool.
And
the material in the septum?
What?
What is the material of the septum?
So the septum also contain neurons as well, but they're just not responding and not receiving the same type of input. They get mostly input from a different thalamic nucleus, which is called POM, which is a different thalamic input station.
And they don't have any synapses to the neurons?
No, of course they are connected. Yes, they are connected.
Okay.
But you can separate them. You can tell which one is a septum and which one is not.
But so these people who model these things believe that even though they ignore, I don't know, at least 50% of the cells and many of
because
the
you mean 50% of the 50% because of the septum?
Yeah.
I don't think they ignore it. They kind of the problem is with POM is it's a very, very difficult so with the barrel cortex this is a classical example. You put an electrode in a cell, you move the whisker, you get a response. It doesn't matter if it's layer 2, 3, layer 5, layer 6. In each one of them you'll get an EPSP. Okay, if you put you try to do the same thing in the septum, you don't know what will excite a neuron. You can spend like 3 hours, you won't get one spike. So it's very difficult. People really don't know what actually activates it. It could be pain, it could be something that comes from the cerebellum. People really don't understand exactly what drives them. Okay. Okay, so plasticity. So experience-dependent plasticity. This is one of it's a very important topic in the sense that one of the key features of the brain is that it learns, and also that it is plastic. And whether these two things are related to each other is a big question. We don't really know, but they both exist. People really strongly believe that they are related, and that's a reason to study experience-dependent plasticity. So barrel cortex is a system that was one of the first systems to show that it was also, of course, shown in visual system with the critical period, which you probably talked about, right? When you study visual systems, so here's an example where you take a rat and you have you record from barrel D2. One of the advantages, as I showed you before, is that you can, different to visual system where you put the electrode and then you have to start mapping the receptive field and find out where the neuron actually receiving the information from and what orientation it responds to. In barrel cortex, you can do that before you put the electrode in, so you can start immediately, and it's a big advantage technically. Okay, so here you put an electrode in barrel D2 and record activity from spine. Okay, now you stimulate D2 whisker and you get responses. Okay, you stimulate D3 and you get some responses but less, as I told you. You get less responses from neighboring barrels. If you stimulate D1, you get also very weak response, not very strong one. Now you do the following. You stick with glue D2 to D3. Okay, just put super glue and stick the two whiskers together. And you wait 62 or 64 hours. Okay, and then you come back and do the same experiment. Okay, and what happens is the following. First of all, the responses to D2 are stronger. Okay, the responses to D3 are much stronger. And the responses to D1 are not changed. Okay, what can we conclude from that? So the conclusion is that the fact that you pair them together actually change the functional properties of these of the neurons in this column. So you still record from the same column, but the functional properties of the neuron have changed. Now, obviously, you understand that two things. First of all, this is not exactly the same neuron, right? Because you cannot, at least back in Modena 93, you couldn't do that. So the fact that this is stronger might be, could be an artifact. Actually, I'm not sure. Maybe it was. I have to check them. But the idea is that by pairing the two together, so what does it actually mean that they are paired together? It means that every time the D whisker moves, right, this neuron is activated. Why is it activated? So during this 64 hours period that you wait, what happens? Every time the D3 whisker is moving, right, even if just the D3 whisker was moved, okay, this neuron was activated because the D3 whisker is paired with the D2 whisker, and the D2 whisker is activating the barrel. Okay, so it will be activated. So this is kind of creating a Hebbian plasticity, if you like. Okay, I pair the activity of the D2 whisker to the activity of the neuron, and then indeed the activation to D3 is now enhanced. Okay, so this is kind of Hebbian plasticity. And the D1 is a control because the D1 was not paired with the D3, and it's not, with the D2, and it's not actually responding. They changed the response. So this is a control that indeed the plasticity was related to the fact that you stuck the two whiskers. Okay, a different way to look at it is the following. So again, this is the mapping of inputs that's going from the thalamus to layer 4 and going to layer 2-3 and then spreading sideways. This is all the things that we've seen before. But if you now do the following experiment. So this is taken from a review paper about this topic. If you take here the area of the yellow area is the area on cortex that would respond to flicking of D1 whisker. So for example, if you move D1 whisker and put your electrode here, you will get some responses. If you go to the other end of the C1 barrel, you would not get any responses anymore. Okay, so this is a control. So the red one is the area that responds to the E1 whisker flicking, and this is D1 and this is C1. Okay, now you do the same experiment, mapping, but after you remove all the whiskers except the D1 whisker. Okay, so you leave the rat only with one whisker for a while, for a few days, and then you do the mapping. And what happens is that the area in cortex that is responding to the flicking of D1 is expanded. So as if the neurons in other places in the cortex are now also receiving information from the D1 whisker. Okay? If on the opposite you're doing the following, you put the animal in maybe this is better. You cause artificially over stimulation of D1. For example, one way to do it is to put some metal beads stuck to the whisker, and then the animal is in a cage where it has a magnetic flow. So it's every now and then you flick the whisker and you kind of stimulate it more. What happens is the opposite. So here it expanded and here it actually shrinks. Okay, it's actually much more limited to the D1 barrel, and actually the others could a little bit expand, but maybe not so significant. You can also get similar results if you put the animals in an enriched environment. So you put them in a cage with all kinds of bells and brushes and all kinds of things that they will touch with the whiskers all the time, and they will become, also the area will become shrink. So what does that tell us? It tells us that, or at least the way people think about it, first of all, is that the cortex is plastic. It can change the receptive field by experience. Okay, this has huge consequences. Today, it's almost obvious, to you that you already learned on brain-machine interface and stuff like that. But the whole idea started from there. The idea is that the cortex can actually change its response because of experience, and we can build on that in some way. That's what I wanted to say about it. Okay. One last note about that is something that I wanted to show you that I think probably is too shy to show you. It's a paper from his lab that was published last year, and it's very impressive, at least technically, and also kind of, in what you could start imagining doing with this technique. And the idea is the following. What you do now is that you take a mouse and you stimulate you stimulate the whiskers, one on the contralateral side. Okay, so if you record from a neuron on the right hemisphere, you stimulate on the left hemisphere and compare it to stimulation of the right hemisphere. And what you can see is that this neuron is not responding at all to the ipsilateral, so it's not responding to stimulation on the same side of the whiskers, which are on the same side of the brain as this one, but it is responding to the other one with a very precise spiking every time you do it. So these are triangles, and these are individual spikes, and this is what you get. Now, this is done with a pipette, with a glass electrode. And this glass electrode, what is special about it is that it doesn't contain only the usual solution that's used for recording, plasmids of DNA. And at the end of the experiment, after you do the simulation, you can electroporate, you can kind of make a buzz of electrical current through the pipette and make a small tear in the membrane, and the plasmids go into the cell. Okay, so what do these plasmids encode for? In this case, they chose just GFP, so it's green fluorescent protein. Okay, and what is the advantage? The advantage is that if you come 2 weeks later, this neuron is now expressing GFP. Okay, and you've already been in his lab and you saw the 2-photon microscope, so you know that if you recall if you have a neuron expressing GFP in the brain, you can see it with the 2-photon microscope. But the point now is that you can go with an electrode and point it back under the 2-photon microscope back to the same neuron that you visited 2 weeks ago. Okay, so you can actually go to a neuron, record what it's doing, and then come back to the same neuron. It's one neuron out of billions, remember. Only this neuron, and record what it's doing now. Now, in this case, this is just a control figure to show that the electroporation of the GFP did not do anything to the neuron, because it's not responding again to the ipsilateral, and it's responding very similarly to the contralateral. Okay, so this is just a control, but you can now, imagine what other things you can do with it. First of all, in terms of plasticity, but for example, you could imagine now I'm trimming some of the whiskers here and going back and see if that's going to change something in the response. Or you can imagine what you can do with putting different kinds of DNA into this neuron. And again, you can do all kinds of things like, I don't know, knocking different ion channels, blocking synaptic transmission, you name it. Anything that could be done with DNA could be done in here. Okay, so unfortunately, I won't have time to talk about all the other slides that I have here. So we'll have to stop here. This is tricky, but that's life. It's on the presentation. If you ever have time, you're welcome to look at these papers. They have the reference, and we meet next on the paper.